So let's start our beam flexural example. This is a floor plan that we see here on the left. So you're looking down. The little boxes are, of course, the columns here. Let me get a pen. We've got beams running in this direction, where I'm highlighting them in blue. And those beams are 6 by 12. So it's nominal 6 by 12, hem fur, number 1. Okay. Then we've got in the other direction, we've got the joists. So those are running in this direction. And those are 2 by 8, hem for number 2. And they are at every 16 inches, so 16 inches on center. We are going to go ahead and figure out the demand side of the equation, and then we're going to figure out the strength side of the equation. And of course, this is going to be adjusted. So this is really the adjusted strength, all those C values. They're adjustment factors, and we need to make sure this is true. So I'm going to start with the joists, and I'm going to and flexure. So we're going to go ahead and do part A here in this video. The next video, I'll probably move on straight into the joist bending stress capacity, and then we'll come and do the beams. Okay, so what do we have here? We are going to have to figure out for the demand, that's what loads are going into this, and so what kind of capacity are we going to have to deal with that essentially. So we've got dead loads, we've got self-weights, and we've got live load. So we'll have the self-weight or dead load of the beam or joist itself, in this case the joist. We will have the plywood decking, carpet and pad, the ceiling, miscellaneous, mechanical and electrical, and then we will have the live load. So we'll have our various superimposed loads, and then we have our live load, superimposed kind of off and on load. You've covered loads in your structural analysis class and your concrete class, and if you've had steel, you've probably covered it even in more detail. So we just need to go figure out what each of these loads are. To go ahead and start getting that demand side of the equation. Plywood deck, most of this stuff we can get out of the ASCE 7. So ASCE 7, you should have bought that. You definitely will need this for senior design. For my class, you don't need it because I'm going to give you the table you need. So I have uploaded table C3-1, which is basically the loads. Okay, so it's the standardized design loads that you can use for different materials. Carpet and pad is not in there because this comes from the manufacturer. We're going to use 2 pounds per square foot, which if you don't know what it is, what it's going to be, that's a reasonable assumption for your first iteration. Once you know the actual final design values, then you go back and you make sure your self-weight's right, you make sure any other things you've assumed are at least conservative, and adjust accordingly. Okay, so this table is uploaded to the Canvas site. So you will want to go look into that to find these values. I will start in this problem and fill in these values, but that's where they're going to come from. Okay, so let's start with our joists, the 2 by 8 hem fur, and they are a number 2. All right, so let's go with joists. And we're looking at the demand side of the equation, in other words, the load side, okay, the application side. So the first thing we're going to need to do is use our supplement to figure out our values, because we need a self-weight and we need dimensions and some things like this. So the place where you want to go first is into your chapter 3 of the supplement. And in chapter 3, there's some intro material, and then it sounds a little weird, but tables 1A, B, etc. So one of the things we need is supplement, and I'm not going to write all this out each time, but since it's our first time, go into supplement, go into chapter 3, and then we're going to go take a look at table 1B. Okay, table 1B is called Section Properties of Standard Dressed S4S so all four sides dressed, sawn lumber. And we're in the sawn lumber example section, so that's what we've got. So if I go into that table, it'll give values for each of the dimension sizes. And if I look in at a 2x8 in that table, 2x8 dimension lumber, okay, if I go across there, it's going to give me the standard actual dress size. Say for a 2x8, it's 1.5 by 7.25. It gives me that area. It gives me the modulus, moment of inertia, the section modulus, moment of inertia, and then it's going to give me approximate weight in pounds per linear foot based on the density of the wood. Okay, and the density depends on a couple things. One is the moisture content, and then the other is the specific gravity for the type of wood you have. So I'm going into all these tables with 2.8. One of the first things, and this is also in chapter 3 of the supplement, is I need to figure out the density. Okay, so the density in, I'm just going to label it density for now. Density in pounds per cubic foot from equation 3.13, which is in the supplement. If you go in there, you'll see that equals 62.4, right? That's the unit weight of water, times G, which is the specific gravity of the wood, over 1 plus G times 0.009, which is just a constant, times the moisture content. Okay, this whole thing, and I should have left myself a little bit of extra room, that times, so all this would be in a row, 1 plus moisture content over 100. All right, so we need G. Where do I get G? I get that from table 4A of the supplement. And you want to go in and take a look at that. So if I look into table 4A, which is in chapter 4, or I'm sorry, yes, chapter 4. Chapter 4 is the reference design values. So chapter 4, I should say supplement, chapter 4 is reference design values. And 4A is for visually graded dimensional lumber, everything but southern pine. So we've got something that's not southern pine. If I go into that table, go take a look at table 4A. Right, so all this is in the supplement because we're just looking for values. Just have your code on the side. If I go in and I look specifically, there is a heading for hem fir. And there is select structural and then the different grades. We have our joists for 2x8, hem fir. I should have written this at the top in the beginning. Number 2. Okay, so if I go in to look at hem fir, what you'll see is that the specific gravity actually is the same for all the different grades because it's the same tree, it's just different quality, right? So if I go in there, I find out that the specific gravity is 0.43, and that's what I'm going to use in the equation. Moisture content, we've said that we are looking at 19% or less from dry wood, and we are looking at dried structural wood here. So it's 19 or less. So we'll just use 19 in our equation. So then we go in, get density equals 62.4, and then I'm going to have G 0.43 over 1 plus 0.43 times 0.009 times the moisture content, and just watch your units with what the equation exactly says. And then I get 1 plus 19 over 100. And I come out of there with a density of 29.7 pounds per cubic foot. All right, I now will go into table 1, back to table 1B, because it's going to give me the weight I need. And all this is to find the weight. So, if it's concrete, what would 150 pounds per cubic foot times the volume we have, or the area and over the unit length. Here, each species is different, so we've got to go look and figure out the density of these species, and then we can go and figure out the weight. All right, so if I go back to Table 1b in Chapter 3 of the supplement, I will see that, I'm kind of following along here too, if I go back into that table, it will tell me that I have approximate weight in pounds per linear foot of piece when density of wood equals, and it gives me choices, 25, 30, 35, 40, on and on. So this doesn't have to be totally exact. This is around equal to 30 pounds per cubic foot. If I was landing dead in between the two or something like that, just linearly interpolate. You know how to do that. And so I'm going to use the 30, and if I go and look at a 2x8, I get a value of 2.66. So from there, I get a weight equals to 2.266. Let's just say 2.3. Why is it okay in this case to just say 2.3? Other than, like when do you say when it's close enough or not close enough? Well, what have we assumed here? We've assumed moisture content, and that's going to vary a little bit. There's some variance in here. We probably don't need to go out to the thousandths place. So this will work for our wood design. All right, so now I have a weight of my board. All of this was to get the weight of the board because I need the weight of the board to have my self weight to go into the load side. So this is the self weight. So now let's figure out what it is for all these other things. So I've got, if I go back here, I need plywood, carpet, ceiling, miscellaneous, M&E, and LL, and live load. So first, let's, I don't know why I wrote a P there. Oh, for plywood. So we have 3/4 inch plywood. And this is where you go to ASCE 7 table. ASCE 7 table C3-1. That's on Canvas. It's with the note packet. Okay, so the handout area. So we're going to go into that table, and that has the values for various materials. And so I'll let you go in and hunt this down, but for plywood, it is 0.4 pounds per square foot per 1/8 inch thickness. Okay, unlike the sawn lumber, plywood, if it says it's 3/4 inch plywood, it's 3/4 inch plywood. So it's 3/4 inches thick. So 3/4 inches equals how many 1/8 inches? And that would be 6. Okay, so I need to have 6/8 times 0.4 pounds per square foot, and I get 2.4 pounds per square foot for the plywood. Carpet and pad, we said we're going to use 2 from the manufacturer, 2 PSF. As you can imagine, different carpet styles and different pad thicknesses can really have a different weight. 2 is a good starting point. Ceiling. If we have 1/2 inch GWB, which is gypsum wallboard, by the way. I guess I could write that out. Gypsum wallboard. Look it up on Google and you'll recognize it when you see it. That is 1/8 of an inch. For every 1/8 inch, you get 0.55 pounds per square foot. And our ceiling is 1/2 inch, so 4 times 0.55 equals 2.2 pounds per square foot. And finally, we have M&E. miscellaneous, mechanical, and electrical, and that's all the other stuff you're gonna kind of hang off of here. You know, it depends on residential and what have you. But in addition to the known kind of additional dead load, we're going to add in 5 PSF from the table. And then we're ready to add up our weight. We know our live load was for an apartment building. So that gives us all. I apologize, my microphone's doing something weird. I'll try to hold still and see if it gets better. Okay. For our live load, we have an apartment building. Live load. So this is all of our dead loads and self-weight is what we've done here. Now we need to look at our live load, apartment building. This is ASCE table 4.1, and that will also be uploaded to Canvas. You'll find it in the same place as the notes and the other table. And I get live load equals 40 pounds per square foot. So the live load per joist is going to be the 40 pounds per square foot times 1.33 feet. I'll let you think about where that came from. How much 1 1/3 feet? So think about 16 inches. That's where my 1 1/3 feet is coming from. There's 16 inches on center equals 1.33 feet. So if I am looking at a joist member or beam member, it's from this one to the next one, right? So I go from here to here, halfway. He gets to carry all that load. So he's going to carry all that load from the flooring system, as well as his self weight, as well as the live load that's on that piece of flooring system. Okay, so at 40 times 1.33 feet, I get 53.2 pounds per linear foot, right? Pounds per linear foot is what I'm doing with the PLF thing. I know some of you, this is old news. It depends on if you've had me for class. It depends on how many design classes you are. So I'm being a little explicit and spelling stuff out here for this first example, just to make sure we don't trip up on any kind of nomenclature stuff. All right, so let me grab another piece of paper here, electronic paper. Let's do our summation here. So self-weight plus dead load, we're going to have 2.3 pounds per linear foot. That was the self-weight. Plus, I've got 2.4 plus 2 plus 2.2 plus 5. That is that 1.33 feet, right? That's that contribution of the floor system load to the joists. Whereas this is just the linear self-weight piece of the joists. And I'm going to get 17.8 pounds per linear foot. And then let's add those two together. So my total weight on the floor, remember we're not factoring loads. So my total weight on the floor is that 17.8 pounds per linear foot plus 53.2 live load pounds per linear foot, and I get 71.0 pounds per linear foot. So now I'm doing flexure, so let's figure out our moment. Moment for these are simply supported. We assume these are simply supported, WL squared over 8, right? Or go do statics if it hasn't been in a while, and the max moment's at the center, and that's the WL squared over 8. At the edges, it's 0. So we're looking for the maximum moment. And that gives me 71 times, these are 10 foot long. If we go back to our problem statement, this is the joists go in this direction. They're 10 foot long each. Okay. All right, so they're 10 foot long, squared over 8, and that gives me 887 pound feet. Now, usually we go straight in with the moment, and we compare it to M sub n and things like that. We are doing stresses now. So the demand side, stress and bending, little fb is the moment. Oops. The moment divided by the section modulus is equivalent to my over I. All right, now I go into your design standard. And you go ahead and go in there too. And you're going to find that you get, so page 15, the NDS is where that equation comes from. We know also that S is BH, or I'm going to use D because that's what they use in the design standard typically, is BD squared over 6, right? All that is I over Y. And from there I get 1.5, and put everything in feet. I'm sorry, putting everything in inches here, over 6. So B, what was this? This was a 2 by 8. So B is 1.5. D is 7.25. Those dimensions are given in the table, same table where we got the weight based on density. And you also know how we do dimension lumber now. And we get 13.14 inches cubed. And that is actually SXX. So it's in the strong axis direction, right? So there would be, if I went in the weak axis direction, it would be a smaller S value. So now I go back to table 1B of the supplement. Which is in chapter 3. And I get F sub B equals, sorry, table 1B of the supplement will give me that value directly. So I can calculate it, but you can also just go straight into the table. So I just calculate it this time. F sub B is M over S. Couldn't read my notes there. 887 pounds per foot. 12 inches per foot. Those are those little chicken tracks there. And 13.14 cubic inches, because I had to do an inch foot conversion there, and I get 1810 psi. And that is our demand, or the max allowable bending stress. Yeah, I should probably not shortcut that one there. Max allowable bending stress. In other words, that's our demand side of the equation. Let me move this up so you can see a little better. Okay, so this is the value we were trying to find on the demand side. And let me circle that. So this is for the joists. And I'm going to stop here, and we're going to go do the strength side of the equation, the stress that we can actually take with the adjustments.